everybody, it's Mr. Crisanti. Mr. Walsh is dead. Anyway, sorry to hear that. Anyway, we're going to talk about stoichiometry today. Now, remember, when you guys learned about moles, what you were really doing was learning how to count atoms, molecules, ions, any chemical unit. So you were learning how to count them. Why do we want to count atoms, molecules, ions, and stuff like that? Well, we want to count them so we can make predictions. And we're going to use this thing called stoichiometry. That's right, stoichiometry. This is going to be your new favorite word, stoichiometry, to make predictions. We're going to use atoms and molecules and ions. We're going to use moles to make predictions. Now, what kind of predictions do we want to make through the method of stoichiometry? Well, let's say we have a chemical reaction. So here's a chemical reaction, and unfortunately, it's not obeying the law of conservation of matter, so we've got to balance it. So we're going to put a 2 right there, we're going to put a 2 right there. Now it's a balanced chemical equation. So we balance the equation, there it is, nice and balanced. Whoops, got to put a parenthesis around there. Very good. Okay, so we would like to be able to make predictions about this chemical reaction, which we represent with the chemical equation. So let's say I'd like to produce a certain amount of water from this reaction. How much hydrogen would I need to do that? Or possibly how much oxygen would I need to do that? Well, we can use moles and the method of stoichiometry in order to answer that question. So, first we have to review what a chemical reaction or a chemical equation is telling us. We know that the coefficients out in front are telling us that this is 2 molecules, this is 1 molecule, and this is also 2 molecules. Which means when one molecule of oxygen reacts, it requires 2 molecules of hydrogen to react with it, and we'll get 2 molecules of water. So that's what this equation is telling us. So if that's true, and it is, and this relationship should never change for this reaction, and it doesn't, that means if we have 10 molecules of this, if all 10 molecules of oxygen react, it's going to require 20 molecules of hydrogen, and will produce 20 molecules of water. Makes sense, right? If it's a 1 to 2 relationship, this always must be 1 to 2. And if this is a 1 to 2 relationship, this must always be 1 to 2. Well, instead of 10 molecules, let's say I have 6.022 times 10 to the 23rd molecules, which everybody in the room knows that this is a mole. So if I have 1 mole of molecules, 6.022 times 10 to the 23rd, 1 mole of oxygen molecules, how many hydrogen molecules will it take? Well, if the relationship stays true, and it does, it should be 2 times 6.022 times 10 to the 23rd molecules, which of course, as we know, is 2 moles. I think you get the picture. And so, in terms of the water, 2 times 6.022 times 10 to the 23rd molecules should be produced. Or in other words, 2 moles. So, this is a molecular relationship, but it's also a mole relationship. So for every 1 mole of oxygen that reacts, it's going to require 2 moles of hydrogen, and you will end up with 2 moles of water. So, what we like to call this relationship, we like to call it the stoichiometric relationship. We're going to use the stoichiometric relationship in an attempt to make predictions, as we were talking about before. Like we said, if a certain amount of water is formed, let's say we want 10 grams, how much hydrogen would we need to actually produce the 10 grams of water? So, we're going to need 1, the stoichiometric relationship, and we're going to need our ability to convert moles. So let me erase this, and I'm going to change this from a molecule relationship to the stoichiometric relationship, and we're just going to dive in and solve a problem, and that's the easiest way to do it. So we said we're interested in being able to figure out how much hydrogen is required to produce 10 grams of water. Okay? So, in any stoichiometry problem, there are 3 steps that you need to do. There's only 3 steps. Count them. 3. There's 3 steps that you need to do. All right? Step number 1 is convert to moles. So whatever you're given, you convert that to moles. That's the first step. So we got 10 grams of water. We're going to convert that to moles. Of course, we do that by multiplying it times 1 mole of water divided by the molar mass of water, which is 18.02, I'm sorry, 1, no, it is 2, sorry, 2 grams of water. Now, this you should be able to figure out because you already know how to find the molar mass. You know that this is the mass of 1 mole. You see that this is very similar to a metric conversion, like a dimensional analysis, because grams of water is on the bottom, so it cancels with grams of water, and we have moles of water on top. So, step 1, we convert to moles. Step 2, we're going to go, again, we're going to go and convert from moles of what you know to moles of what you're looking for.
Now this is the step that makes it stoichiometry. This is the step that makes it different from mole to mass conversions that you've been familiar with thus far. We are going to be using the mole ratios from the balanced chemical equation to convert from moles of one substance to moles of another substance.
So there is Mr. Walsh back from the dead. So Mr. Walsh is absolutely correct. We're going to use that stoichiometric relationship between hydrogen and water to actually convert from moles of water to moles of hydrogen, which we said we're going to do in the second step. Now, you have the second step. Unfortunately, where I wrote it, I didn't leave myself a lot of room, so I'm going to have to erase that second step. So shut off the video, or actually stop it, pause it. You don't have to do that, but you guys out there in chemistry land, pause the video, right? Pause the video, pause, positive, pause the video, okay? And write that down, and I'm going to erase it. Okay, so we're going to multiply it times the stoichiometric relationship between water and hydrogen. Now I'm going to want the 2 moles of hydrogen on top and the 2 moles of water on the bottom because I want the moles of water to cancel out.
And once again, those are from the coefficients from the balanced chemical equation. The 2 and 2 are the same 2 and 2 you see in front of.
Yes. Perfect. All right. Now, last but not least, in the third step, step number 3 says convert to whatever. And when I say whatever, I mean whatever the question asks you for. So remember, we wanted to know the amount of hydrogen. Well, we could figure out the amount in moles, or we can figure out the amount in grams. So if you're asked for grams, you're now going to have to multiply this times the molar mass of hydrogen, which is 2.02 grams of hydrogen for every 1 mole of hydrogen. So moles cancels with moles, moles cancels with moles, grams cancels with grams, and what does this come out to be?
1.12 grams.
Comes out to be 1.12 grams of hydrogen. So, in order to produce 10 grams of water, it requires 1.12 grams of hydrogen. Now, there's one thing that I did not mention to you. We are making an assumption when we do this kind of a problem. We're assuming that the hydrogen is in excess. In other words, we have an unlimited amount of hydrogen. I'm sorry, not hydrogen, oxygen. Sorry about that. We know that the amount of oxygen is never going to run out because there's more oxygen than we actually need. This is limited. We know we need this much hydrogen to produce that much water. The oxygen is in excess. So when we're doing these kinds of problems, when you are given a single quantity and asked about a single quantity of something else, we assume that other reactants are in excess. Now, we're going to do another another video in which they're not in excess. And that's all for now.